We've got a gravity question here. Every year they've asked a gravity question, so don't be surprised when it comes up again this year. This one's the Earth, a satellite going around the Earth. It's in a geostationary orbit. As you're reading your questions very carefully, you've noticed that, and you know with a geostationary orbit the time is equal to 24 hours. It takes 1 day. It remains vertically above the same point above the equator. We've got the mass of the Earth, radius of the Earth, the satellite's mass, and they've given us g, the constant. Alright, calculate the period of the orbit of the satellite. A whole lot of students just launched into this one and started writing t equals the square root of da 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 da, and using the big formulas with their formula sheet. But you've got to look, it's only worth 1 mark. Only worth 1 mark. And the answer's up there in the question there. It's a geostationary satellite, 24 hours. All they want is they want it in seconds. So not this at all. It's time equals 24, and there's 60 minutes in an hour and 60 seconds in a minute. Times those together, 86,400 seconds. Calculate the radius of the orbit from the centre of the Earth. Now we're doing our calculation. So this is one of these ones where we've got already derived on our cheat sheet, ready to go. Don't have to derive it again. And it's the third square root of 6.7. No. Let's put the letters in first. GMT squared over 4 pi squared, which equals the third square root of 6.67 by 10 to the minus 11. That's G. G's up there, times M. Which M is it? We've got a mass of a satellite, and we've got mass of the Earth. That big M is always the mass of the thing in the middle. So the satellite is going around the Earth, and Earth is in the middle, so in this case it's the mass of the Earth, 6 by 10 to the 24. 24 times the time we've worked out, 86,400 squared. And then we divide by 4 pi squared. Once we've set that up, it's as easy as dividing it out, well, working it out, but this is one that always gets students is trying to get it on their calculator. I do top in brackets, divide by the bottom in brackets, then I push equals, and then I do the third square root of afterwards. Okay, make sure you've got these brackets around the top, especially the brackets around the bottom. Really important to get the brackets around the bottom. Push equals, and then I do third square root of. And the answer I get is 4.2 by 10 to the 7, which is about this many meters. That's rounded off, of course. But it looks nicer for me to put it in the scientific notation. And the last one in this set. Yep, here we go. An astronaut of mass 65 kg is on board the satellite. She's interviewed on television and says that she is weightless. Explain how the terms weight, weightlessness, and apparent weightlessness either apply or do not apply to the astronaut. So on your cheat sheet somewhere you might have definitions of what all these are. Weight, weightlessness, apparent weightlessness. You've got to read the question very carefully, and it says, do they apply to her or do they not apply to her, and explain how. So we're going to be there's 3 marks, and there's 3 terms to talk about. So I really want 3 dot points with each one of those. Let's just set them out like this. Dot point 1, weight. Does this apply to her? Does this not apply to her? Yes, she has weight. Yeah, she has a gravity force still. Even in orbit, she has a weight force. She has a weight force. And that is because she's still in the Earth's gravity field. She's still in a gravity field. Right, weightlessness. Is she weightless? No. This doesn't apply to her. Oh, no, she is not. She is not weightless. She would need to be outside a gravity field. Have no gravity force on her. And the last one, apparent weightlessness. Weightlessness. And this is the one that she is, yes. So she has weight, but she appears to be weightless. She does have apparent weightlessness, and let's explain why or how. Because she's in free fall. In orbit, you're in free fall. Because she is in free fall, and in that case, therefore, she has no normal force. Has no normal force. There we go.